Recording in progress.
All right, folks, welcome back to our conversation about equilibrium stoichiometry and when it is appropriate to apply the small x approximation. In our last conversation, we looked at a situation where the equilibrium constant was incredibly small, meaning we could assume that the change in the concentration of reactant going from initial to equilibrium conditions was very negligible, which allowed us to simplify our solution for x by kind of sidestepping around that quadratic formula use. And now we're left with this question of what if the equilibrium constant is large? So let's kind of hash through this like on a conceptual rational level. Like let's kind of trust what our understanding of equilibrium tells us about what it means when our equilibrium constant is large. So we started this discussion by saying that when k is large, and here we've got much greater than 1, but let's go ahead and use our 10 to the 5. So very big. We know that this reaction at equilibrium is incredibly products favored, meaning there is an overwhelming or very, very large amount of products relative to each reactant at equilibrium. And my question for you is, have we seen in our chemistry careers a chemical reaction that winds up with a huge amount of product compared to the amount of reactant that was present to begin with? And if you think back to your Gen Chem 1 journey, you'll probably realize that, oh, yeah, that's how we thought of like every single chemical reaction. So when we've got these equilibrium constants that are really large, we are going to treat the reaction as if it proceeds to completion, meaning like all of our reactant undergoes its, limiting reactant stoichiometry to create our theoretical yield of product. And then the reaction stops, right? Like that's how we thought of chemical reactions in Gen Chem 1. However, we now know in Gen Chem 2 that there's really no such thing as the point at which a reaction stops. So we are going to treat the reaction as if it proceeds to completion. And this like completion state is what we are going to call the initial conditions before we achieve equilibrium. Because once we've like allowed in our mind conceptually for this reaction to fully complete, we now recognize that it's going to shift backward just a small amount to achieve an equilibrium. So once we've established our completion, which we're calling our initial conditions, we know that achieving equilibrium is going to happen by increasing the rate of the reverse reaction, which will decrease the amount of product made, as well as increasing the amount of reactant present. So the idea is, again, we figure out what's going on once the reaction has gone to completion, just like we would in Gen Chem 1 stoichiometry. And then once we're at those completion conditions, that's what we treat as our initial conditions in our ICE table, because we have the reaction that's like fully product driven, and then very, very slightly going to shift away from that pure product only situation when it gets to equilibrium. So this means we have to remind ourselves of how we do our Gen Chem 1 reaction stoichiometry. So this requires us our kind of classical stoichiometric treatment. So this requires us to do some limiting reactant, LR, stoichiometry. Because at the end, quote unquote, of the reaction, we have a theoretical yield of product, which is determined purely by which of our reactants was the limiting reactant. We also know that at the end of reaction, so again, what we're calling like this completion state, we know that the limiting reactant is completely consumed, meaning its concentration is equal to 0. That's how we define the limiting reactant in Chem 210. We said it was completely consumed and stopped the reaction upon its consumption, which means that also at the end of the reaction, we have some amount of our non-limiting or excess reactant left over. So all of these things are things that we need to calculate and then put into the I column in our ICE tables. So we've got to figure out our theoretical yield by doing our limiting reactant analysis. We have to figure out the amount of limiting reactant left at the end of the reaction, which we know should be 0. And then we have to figure out the amount of excess reactant that's left over at the end of reaction. Once we have those conditions, we have the initial conditions of our reaction, because again, this is a reaction that is incredibly products driven at equilibrium. So it's like almost behaving as if it is gone to completion. And then once we have all of this information as our initial, then we use an ICE table and look for where the small x approximation is appropriate. So let's practice this. So we have here a complexation reaction. So the complexation of copper 2 ion with ammonia greatly favors the complex with an equilibrium constant of 5.1 times 10 to the 13. Again, this is a gigantic equilibrium constant. So this is signaling to me that I'm going to have to treat the system as though it has run to completion and then shift it to equilibrium from there. And I was told that I have 20 mils of copper 2 sulfate reacted with 1 liter of this molar ammonia. What is the concentration of the complex that is formed? This does not make sense because I didn't give us the concentration. So let's make our life easier. Let's go ahead and call this 0.100 moles of copper 2 plus. All right, let's start by perhaps writing out our chemical reaction. So we are creating a complex. Let's write our net ionic equation where we have copper 2 reacting with ammonia, which reacts to form this CuNH3 2+ complex. So this is very similar to our iron thiocyanate complexation reaction. And anytime we are preparing ourselves to do stoichiometry, we need to ensure that our chemical reaction is balanced. 1 copper, 1 copper. I am balanced in copper. But here in the complex, this requires 4 ammonia molecules, which means that to create 1 complex, I need 4 NH3s. So let us do our limiting reactant stoichiometry. So this is where we're going to determine our initial conditions, which will be the completion state of the reaction, assuming it completely, like fully runs to make product. So we've got 2 different reactants. We've got the copper 2. So I know that I have 0.100 mole of copper 2 ion. And if I were to convert this all using my mole ratios into complex, I know that for every 1 mole of copper 2 ion consumed, that creates 1 mole of our, I'm going to write complex, meaning I could, if all of the copper is consumed, make 0.100 mole of the complex. And now let's compare this to what we know about the other reactant. So we had 1.00 milliliter of ammonia. And the concentration of that ammonia was, sorry, this is 1.00 liter, was, let's see here, 1.05 moles of ammonia per 1 liter. And if all of my moles of ammonia are consumed, so that is 4 moles of ammonia, then that will generate 1 mole of my complex. So let's figure out what this is. This is 1.05 divided by 4. This gives us 0.2625 moles of the complex. And if we are comparing these 2 mole quantities, we need to figure out which is lesser, aka which one was limited. That will give us the identity of the limiting reactant. So since this value is smaller than the one below it, that means that this had to be the limiting reactant, and this is the theoretical yield. So we have identified of our criteria the identity of the limiting reactant, and in doing so, because we've determined the limiting reactant, we know how much product we can maximally make if this reaction were to run to completion. Okay, so I'm going to just kind of keep a little note up here. Concentration of complex is 0.100 mole over the 1.00 liter. So this is going to be our molarity of 0.100 molar. Okay. What else do we need? We have identified limiting reactant. So we can say that we know that the concentration of copper ion, once this reaction is run to completion, is 0 molar. We've completely consumed it. It was our limiting reactant. We also know our theoretical yields, right? That was what we obtained, the maximum amount of product that could be made if this reaction runs to perfect completion, which leaves behind the amount of excess reactant left over. So I'm going to just kind of remind us, since 0.100 moles and moles of complex made, we need to determine the amount of ammonia that required and then subtract that from the initial amount of ammonia that we had to react in general. So I've got 0.100 moles of the complex. And if, according to my stoichiometry, 1 mole of complex was formed, that is because 4 ammonias came together with the copper to do so. So this becomes 0.400 moles of ammonia. And this is what is used, right? Used, required, same language. So then left over is going to be the initial moles of ammonia minus the moles of ammonia used. So the initial moles of ammonia present, we had 1 liter of a 1.05 molar. So that is 1.05 moles of ammonia present initially, minus the 0.400 moles of ammonia that was required for this reaction to run to its presumed completed state. So let's take that difference, 1.05 minus 0.465. And we are limited to 2 digits after, that is mole. NH3 in excess. So now, our little notebook that we're keeping up here, we know the concentration of ammonia once the reaction has run to completion is 0.65 moles in that liter, right? So this is in the 1.00 liter. All right, that was a bunch of Gen Chem 1 stoichiometry, right? We assume that the reactants completely convert to products and then the reaction stops. That's not how this works anymore, right? We now know that we achieve some kind of equilibrium. So all of this was a means for us of achieving or finding our conditions at our initial pre-equilibrium system. So because this reaction had a gigantically large K, we said, all right, let's go ahead and treat this as if it were a reaction that would go completely toward the production of products. And then that's going to be our initial state from which we shift out of to get to equilibrium. So let's continue this and now do an ice table. So from our limiting reactant stoichiometry, we know the concentration of copper ion initially. So this is the amount that is present. Now we're saying initial, we mean at the end of the reaction. So that's our 0.00 molar. We know the concentration of the complex is 0.100 molar. And then left over, the concentration of ammonia is 0.65 molar. And this is all going to become, again, the initial conditions in our ice table. So I've got my copper ion reacting with 4 ammonias to create our copper ammonia complex. And let's build our ice table. So this is all from the limiting reactant stoichiometry. Initially, the limiting reactant, the copper ion, there's none of it. So at the initial condition of the reaction having run to completion, no copper ion left. It was limiting reactant. And when the reaction has run to completion, what we're calling our initial state now, That means that we've consumed all of our copper, leaving behind 0.65 molar of ammonia and generating the theoretical yield of 0.1 molar of our complex. Now, if we set up our equilibrium table, we know that in order to achieve equilibrium, let's think about this carefully. I have made predominantly product, like I've made completely the maximum amount of product that I can make. We are now going to shift backward. So don't just mindlessly decide that it's going to be plus X minus X, whatever. You need to think about in what direction you're working with here. So it completely ran to react to products. And now we're going to shift back so that we have a little bit of reactant left. So I know that my maximum amount of product is going to decrease by some amount X, which is then going to increase the amount of product present at equilibrium by some amount X for copper ion, because it's 1-to-1 with the complex, and by some amount 4X with our ammonia, meaning that at equilibrium, the concentration of copper ion is X, the concentration of ammonia is 0.65 plus 4X, and the concentration of complex is a little bit less than when we assume the reaction ran to completion. Let's ask ourselves a question. Which of these x's can be approximated as 0? Let's think about this. Our K is incredibly large, meaning that this initial state of having the reaction run to completion and the actual amount of our product that's present at equilibrium are not going to be different from one another. I mean, they are, but not like a noticeable huge amount, not within 5%, right? So I'm going to go ahead and assume that this decrease in our product in this incredibly product-driven equilibrium is about 0. X is so small, it could be approximated to 0. What about over here? So what about what's going on with our reactants? So let's look at what we have in this particular reaction, because this kind of analysis we're about to do is going to be like one that you have to do on a reaction by reaction basis, right? So here, notice I had a really overwhelming amount of excess reactant, right? Like an incredible amount of excess compared to the copper ion. Like this was just a gigantic amount of ammonia. So if I think about how that amount of ammonia is going to increase from the completed reaction state to now this shifted toward reactant equilibrium state, even though it's 4 times that change X, it's still going to be something that's really small relative to the amount of the ammonia that's present here. And I'm going to just make a note here. We can only do this for the ammonia because the concentration of ammonia initially is pretty dang large, right? We had a huge amount of excess. So that means that we can knock out this and this, leaving our equilibrium calculation to be K is equal to concentration CuNH3 or 2 plus over concentration Cu 2 plus times concentration NH3 to the 4. This K value had a value of 5.10 times 10 to the 13. And if we plug in our equilibrium concentrations that we have obtained using our ICE table and also applying that small x approximation, in the numerator, this becomes 0.100 molar. So we're assuming that there's no real appreciable change in our product concentration for this incredibly products-driven equilibrium over x times, again, the presumed constant, approximate constant amount of excess reactant that is left over at equilibrium. So we're assuming that the 0.65 molar that's left over once the reaction has completed, and then the amount of that molarity that's like changed or increased when the reaction shifts left, create some product, or sorry, some reactant, that's going to be also very small. This is to the 4th, right? Can't drop our exponents. Okay, I'm going to do a neat little trick. I'm going to take this, and I'm going to swap them. This is fraction rules. A over B is equal to C. I could multiply both sides by B if I wanted to, or cancel B. And then I could divide both sides by C, which would leave me with A over C. All this is to say is that if you've got a fraction equal to a number, you can simply swap the position of the denominator of that fraction in that number, and that is algebraically legal. And you can check it by doing kind of what I just showed. So I'm going to swap the x and this. So I've got x is equal to 0.100 molar over 5.10 times 10 to the 13 times 0.65 to the 4th. So let's figure out that denominator. So 5.1 times 10 to the 13 times 0.65 to the 4th. And then I am going to take my 0.1 and divide that value into that. So I get x is equal to 1.098. So I'm going to call that 1.10 with sig figs times 10 to the negative 14 molar. Notice this is an insanely tiny amount of copper ion, right? Like that's what we're saying here, is that this amount is what's present in equilibrium. And you could prove to yourself that if you were to like, you know, quadruple this and then add it to here, that to the significant figures of this problem, it'd be 0.65. So this is the beauty of the small x approximation. I suggest, if you want to confirm this for yourself, that you go ahead and do it the full algebraic way. So you can always verify with the 5% error rule. However, keep note that it's not always going to be a quadratic formula issue. Here we've got something raised to the 4th. So this will give you like a really gross polynomial that if you don't remember how to factor and then solve, you'll probably need to use some kind of computational software to solve for you. So just, you know, don't freak out when you see that. But yeah, here we go. It makes sense. It's very small. This is an incredibly product-driven complexation. Okay. That completes our conversation about just like general chemical equilibrium. In our next topic, we are going to delve into how our principles of equilibrium we've discussed here can be applied to acids, bases, their dissociations, and their interactions or reactions. So coming up next is acid-base equilibrium.